those of you who don't know Dr. Lin, he is one of the tenured faculty here at the Institute for Astronomy. He is originally from Taiwan, where he received his bachelor's degree. He then went to Michigan State University, and kind of an interesting little bit of trivia is that he has the same dissertation chair that I did, Dr. Jeff Kuhn, and so I dragged him onto my dissertation committee as well. After Michigan State University, he got a postdoctoral position at Berkeley, went over to Sac Peak, and then we were lucky enough to bring him up here to Maui. And so he will be talking about his recent South Pole expedition, or not South Pole, Eclipse expedition. Yes, I'm sleep deprived today. He'll be talking about his Eclipse expedition, and if we could give him a nice Maui welcome.
Thank you, and welcome to Institute for Astronomy. And I see a lot of familiar faces here, actually. And again, my name is Haosheng Lin, and I've been on Maui for 10 years. Came from New Mexico, National Solar Observatory in Mexico in 2000, and it's been here since. And one correction, I went to Caltech, not Berkeley, after my degree. So anyway, this is my first public talk, so in essence, it's a little bit of screaming and yelling when you drag me here, just because I was not here most of the time. See if I can get it started. Oh no, it's already started. You got a sneak preview. Anyway, so this is my first public talk, and I'm very happy to be doing this. I should be doing more of this. And this is a good opportunity since we just went to the eclipse, total eclipse in Tatakoto. It took me a while to learn to speak it, to pronounce it correctly. And in July. So what I will try to tell you today is it's pretty much a talk story session, I think. What we did there, our experience, and but before I do all that, I think I should try to give you a little bit of the 1, 2, 3 of the solar eclipse. I'm sure a lot of you here are really interested in astronomy and understand all that how all that works. But nevertheless, I'll just go through it. Then we'll just go through. Pretty much it's a story of how professional astronomers do our plan and execute our research. And this is not as boring as what we do in the lab, where there's no story to tell and no nice picture to show. So I'll go through the decision-making process, how we select the site, the island of Tatakoto. It's a interesting place, and never seen any place like that before. So it shows lots of pictures. Tell you about the experiments that was done there, and the eclipse day, the whole sequence, and then show you some of the results we got there. Okay. Let me see. So we are combining high tech and low tech. There's a laser here, but like I said, that doesn't show up very well in our second life. So that's my low tech pointer. So where did it go? Let's see what happened. Okay, so let's start with the basic of solar eclipse. You may have heard there's a total eclipse, partial eclipse, and annular eclipse. That's a total. That's actually the picture from this eclipse. Okay, and this is what we call the partial eclipse, and this is what we call the ring eclipse. And by name, you can see that the moon isn't big enough to just cover the whole sun. So you still see the limb, the edge of the sun. So you don't get to see the corona in this case, right? Partial eclipse is the moon is not right at the center and just dark is just right. So that's a partial eclipse. So how does this work? So start here. supposed to have a yellow sun here, but I blocked it already. Anyway, the sun, imagine you are here, this is the surface of the Earth, and the sun, so if you are here, you can see the whole sun, right? Now, if you put the moon right in between you and the sun, and this happens from time to time, then this beam will be blocked by the moon. Then you don't get to see anything. The moon itself casts a shadow on the surface of the moon, of the Earth, right? And if you happen to be in here, then you don't see the sun, and that's how you get a total eclipse. This spot is very small. It's only about 270 miles in diameter, the biggest. Okay. And that changed. That's not a fixed size. So that's when you get a total eclipse. Now, now we have a real sun. In the other case, now if you're in another place, then outside of this shadow, the dark shadow, then part of the sun will be blocked. Right? This ray from here will be blocked by the moon, and you only get to see this piece. And it depends on where you are at, actually, how far away you are from the umbra, what we call the umbra of the shadow, the darkest part. Okay. So the closer you get to the umbra of the lunar shadow, then the less sun you can see. If you're out here at the edge, then you see almost the whole sun. Right? Outside of this area, then you see the sun. Sun is not blocked at all. So this is a partial eclipse. And the ring eclipse works when you increase the distance between the Earth and the moon. Right? So then the shadow, actually, the umbra was here, but then you pull the Earth back. So the shadow, now you don't get a complete shadow, but you can still see the edge of the moon. Right? So that's how the geometry works. And again, you still have what we call the penumbra. It's like the terminology we use for sunspots. In this secondary shadow, then you still get to see the partial eclipse. Right? So that's how eclipse works. And I said the distance between the Earth and the moon change. Right? And we know that, well, the universe is not perfect. The orbit of the moon around the Earth is actually not a perfect circle. It's a ellipse, right? And it's pretty close to a perfect circle. So if this is the orbit of the moon, then the Earth doesn't sit right at the center of this ellipse. If you remember your geometry, then in the ellipse there's 2 points in this part. It's called the foci of the ellipse, and the Earth would be sitting in one of them. And this was figured out by the gentleman named Kepler, right? In the 1600s, he first figured out the orbit, how the orbits of the planets around the sun, and how that all works. It got to be a circle or an ellipse. So we have known this for many hundred years now. And so the distance between the Earth, the closest is 356,000 kilometers. The longest is 400,000 kilometers, right? And in fact, the distance between the Earth and the sun also changed. So it's this interplay between the distance of the Earth to the moon, to the sun, and how they got into place, then that's how eclipse happens. Right? Okay, so that's a satellite sequence of the shadow of the moon going through the Earth in eclipse of 2001, going through Africa. That's, if you remember, you can recognize this piece. That's Africa. This is European meteosat. It's a weather satellite. Right? So you can see. So if you happen to be here in this path, then you can see the total eclipse. I said that earlier. The darkest part, where you get a total eclipse, is only about 270 kilometers, the largest. Right? It can be smaller. The shadow moves at a speed of between 1,000 miles per hour to about 2,000 miles per hour. It's very fast. Right? So you can do the numbers and figure out, well, the longest time that the totality, the eclipse can last is about 7 minutes something, and sometimes it's shorter. A lot of times it's much shorter, 2 minutes or so. The eclipse we have in July, this July, the longest, the duration is about 5 minutes 30 seconds or so. Right? And you can see most of the time it goes across the open ocean. So unless you've got a boat, you get into the right place, you don't get to see it. In this eclipse, some of my colleagues actually went to Africa to do it, and I didn't do that. And another adventure was back in the 80s, I think. One of our astronomers, Dang Ho, he's on Big Island now, they actually took a Concorde. Now it's 1,000 miles per hour. Our regular jet, 767, 747, they go at 500 miles per hour only, right? So you cannot keep up with the shadow. But if you take a Concorde, and they actually put telescope on it, so they follow it, and their eclipse lasted about almost 2 hours. Too bad we don't fly that anymore. I would love to do it. We did one in '98. We put our experiments on a C-130, so that's really slow, right? And the idea there was not to follow it, but to get above the clouds. Your biggest enemy during the eclipse is the clouds, right? The weather. So, and it only happens once every 1 or 2 years. Actually, get to that. So you want to optimize your opportunity, and that's something you can do also. Anyway, so that's a neat movie sequence, I thought. So why do you do solar eclipse observation? Right, it's only 5 minutes, 7 minutes the longest. If you can get the B1 bomber today, you can do it for 2 hours. But it's very rare, right? Happens once every year or every 2 years. The next one actually is November 13, 2012. It's going to pass through the northern tip of Australia, and duration is going to be around 4 minutes something. But that's over open ocean again. On land, the longest is about 2 minutes something. Right? And there are lots of ground-based and space-based telescopes that's looking at the solar corona continuously in space. Right? So why do we do this? A lot of my colleagues said, I used to say that too, that, oh, you guys are just going to go have fun, right? Eclipse. Well, what do you do in eclipse that we cannot do on a telescope? And the fact is, there are still many things that you cannot do even with the fancy telescope we have in space, on the ground. The eclipse gives you the best condition for observing the corona. The corona is the outer layer of the sun. It's a very thin atmosphere outside the sun that you don't get to see every day. It's too faint. It's about 1 million times fainter than the sun itself. So it's like, but that's still very bright, much brighter compared with all the stars you can see during the night. Right? So the reason you don't see the corona during the day is because the sky. Well, we hate the sky. We want to suck all the air out, right? Then we don't have the sky. Then we can see the corona all the time, even though the sun is right there. So during total eclipse, then the sunlight doesn't hit the atmosphere, so you don't have a bright sky. That's how you can see the corona. And this condition, and the moon is just the right size. It's just the same size like the sun, or angular size, right? I mean, the moon is smaller than the Earth, about a quarter of the size of the Earth in diameter, certainly much, much smaller than the sun itself. So how does the moon block the sun? Yes?
It gets in front of the sun.
Yeah, but it has to be in the right distance, right? The distance has to be just right. You put it too far away, you get a ring eclipse. You get it too close, you don't see it right up to the edge of the sun. You block this whole sun here, right? So how come the moon is cooperating with us so nicely is that it blocked the sun just right? Is it coincidence? Is it somebody doing it for us, or... No, not the drag. The drag will have an effect on the eclipse. So the it's really a coincidence. It happens just around this time in our solar system's history and the Earth and Moon system's history. It's just at the right distance. Some of you may know that the gravitational drag is actually pulling the Moon further and further away. So I don't know, I don't remember the number, but a few million, 100 millions of years later, the Moon will be too far away. We will never see a total solar eclipse again if we can live that long, right? So it's a coincidence, a nice coincidence for us that the Moon, just the right size, block the Sun just right, so we can see all the way up, really close to the edge of the Sun, and really far out from the Sun also, all at the same time. That's the best condition we can have to observe the corona, right? So, and there are observations that you really cannot do because it's a new observation that we haven't developed the technology to the point that we can, NASA feels safe to put it up there for you, right? So those observations we can only do on the ground today, and to do it, we can put it on telescope, but the telescope would not have the same performance like eclipse condition. So we want to do this during the eclipse. You can also build a artificial moon in the space. There's no air, right, to block the Sun for you. And in that case, then you can reproduce the eclipse condition, except it's very hard. This is a number I worked out. This is well, astronomers has been thinking about this for a long time. So this is your artificial moon, and you have a satellite, another satellite some distance away. If you know what you are doing, you design your telescope to the right size, the artificial moon to the right size, put it at the right distance, you can block the moon and reproduce the eclipse condition in space. Right? So this is a ESA, European Space Agency's mission called PROBA 3. And the idea is to fly 2 satellites in formation, precision formation flight in space, and try to do an artificial eclipse, and then you can have your total eclipse all the time, right? And these are the number I did. So if you want to have a 20 centimeter or 8-inch telescope, not very big, and you want to see all the way up to the edge of the Sun, then you need to put an 8 meter or 320 inches occulter. 8 meter is pretty big. It's the same size as the Gemini telescope, the primary mirror of Gemini telescope. Right? You put it about, what did I say, 8.4 kilometers away. If you can do that and keep them in that configuration, then you can do your total eclipse all the time, right? So the distance, the size of the moon, artificial moon, the distance determines the size of the shadow, so that determines the size of the telescope. And here I'm being conservative. I just say 20 centimeters, this big. For a lot of the experiments we need to do, actually we want a telescope 4 meter big, so you can imagine how you can scale this up. So it's very difficult, right? But we're working on it. In fact, one of the team that went to this eclipse, they are working on an instrument that supposedly will go on this mission. Okay. All right, so that's why we do eclipse. And this is the eclipse path of this July. You recognize Hawaii here, right? So this is, I think this is Tahiti. And you saw the movie how the shadow move across the surface of the moon. First thing we look is where do you have the best chance of seeing the Sun, or you have a best chance of good weather, right? So this is a weather statistic map. Here you have 40% cloud coverage, and it goes up higher. So these are bad places, and this stretch is about, according to statistics, that you have the best chance of seeing, getting a clear sky. So it's right next to Tahiti. Tahiti, unfortunately, just outside the totality path. Right, so people there see a sliver of the Sun, but it's not total eclipse. Easter Island, somewhere around here, this is Chile, didn't have good weather statistics, right? But here they have longer duration. So based on this, I said, well, we should go to Pacific, and these again are climate statistics for July, and this is in Tuamotu Atoll, that's next to the east of Tahiti. So it's pretty good statistics for. I couldn't find these two little atoll on the map, but I found this one. Tue, I guess that's how it's pronounced. That's right here, outside of the Eclipse Path, where they have statistics. The other two I couldn't find on this map. This is Tahiti again. So I fire up Google Earth. I said, where do I go? And you can zoom in and see, oh, this one doesn't have. There's one right at the center, but nobody there, right? It's bare. Look around, I found this one. I said, hey, that has my name on it. I should go there. Turns out this is where the French staged their nuclear test in the 60s, 70s. Okay, so there's a population of 2,000 or so. I didn't notice this one. I thought, well, one of the reasons I picked this one first is because it has a large population. There's a high school, an Air Force base, a hospital. And these two are important because my experiments requires liquid nitrogen. My infrared cameras require liquid nitrogen. So how do you get liquid nitrogen to that place? Well, Air Force base, they would have that if they have some serious jet fighter there. Hospital, they usually would have that. Right? So that was my thinking. It's off to the totality path. It's to the edge, 3 minutes or so. But this is critical. Without liquid nitrogen, I can't do anything. So we started contacting people there, and they said, yeah, sure. There's one, no hotel, there's one bed and breakfast. According to Shadia, she said it's 4 stars, 2 rooms. It's booked already. We started 2 years ago, right? It's booked already. And we said, no, we have a big group. Can we use the school? They said, yeah, sure. They will put us in contact with the school there. And the school there said, well, why don't you go to Tatakoto? It's closer to the path, right? So this is how, and this is where they did the nuclear test, the other atoll. It's very close to the center. Population 250. There's one elementary school, nothing else. Right? But then, well, the first thing I needed to do is find out how I can get liquid nitrogen there. And it turns out Hao doesn't have that either. We have to ship it in from Tahiti. And good thing they have Air Liquide in Tahiti, so they actually have a big plant. They make liquid nitrogen there. So in terms of liquid nitrogen, there's no difference. Then of course we decided to go to Hao, and we made contact with the school there, and they agreed to host us. So that was nice. So that's how we picked the place. And that's the place. So this is 3.6 kilometer. That's about what? 2 miles from here to there. So this is about a little bit more than 2 miles. This is maybe 8 miles. That's the airstrip. That's the little village. And the rest is nobody. It's just the coconuts. You can walk from this side to that side in about what? 5 minutes? A nice place. So here is the aerial view of the village. So if you can read French, that's the school, right? So that's the football field, and this is where we staged our experiment. That's the church. That's the dock they have. That's the one major road going to the airports. You can see the lagoon here. There's an old church they abandoned. The village moved from somewhere there all the way here. So that's the aerial view, and that's the school. Pretty nice, actually. I haven't done this for a long time, but my other colleagues, they go to every eclipse, and they said this is like heaven compared with last time they went to Marshall Island. So that's the school building. That's the office of the headmaster. Then there are 2 classrooms, and then the facility. There's a kitchen, a dining hall. On that side, there's another classroom there. So that's our bedroom. 10 in each co-ed. No options. No hot water for shower. There's one, but only for the ladies. The man has to tough it out. But it's air conditioned, very nice. Yeah. The funny thing is, well, I'll get to it. There's a fun. This room, they turn it off. This is Italian group, and this is American group, and we have it all the time. The computer lab, it's very nice. No internet access. There's no fiber, no cable going to the island. No reason to do that, right? You can buy a USB dongle and get satellite internet very slow for, I don't know, $50, $60 for a few hours. But they are doing very well, I think. That's the village, the church. They keep it really clean. And they still keep the Tahitian, the Polynesian tradition. The community owns the property, and the money is pooled. Right? So they keep it really nice and clean. The people there, that's there. I wonder about it for a long time. They dry their coconut husk for lots of things, and it rains there all the time. So they have to keep it dry. That's the bar. They have 3 of this around the football field for a population of 250. I asked them what's going on. They said, oh, it's a Marcel Day coming up. So they have all this. I thought they just want to feed the tourists, the scientists, and get us strong or something. But no. I thought this is very interesting, the way they did it. So it's very green. Nice pattern with coconut leaves. The post office. Here you can go there and buy a card, and they have a wireless router, and it gives you a password. You can log in and connect with the world. But that place is mosquito infested. I couldn't stay for a long time, but for some reason the school doesn't have any mosquito, and then they all go after me. So I was happy in the school, but not here. That's a plaque for when it was built, I think, September 2006. Some blah, 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 something about the president of French Polynesia was there to dedicate the place, something like that. I like the nice fish and their flower. Anybody know what they call this flower in Tahiti? It's, you get off, and they give every one of them. Tiare? Yeah. It's like their national flower. The people there, I think he is her father, a real nice singer. She's actually at school, the teacher of the school. That's Nono, the headmaster's wife. Nono, I asked her, what does it mean? She said, mosquito. And a day later, I think, mosquito. She said, the insect that bites. Took me a day to figure out what it means. Don't we look like a brother? He doesn't speak English, I don't speak French, so we never really communicate, but somehow it's he's always around helping. That's the whole team. I included our hosts there. They feed us, they take care of us. And let me see. No, that's the school headmaster. Okay.
It's kind of scary.
Yeah. His name I forgot how to pronounce already. But they speak Tahitian. They are not. They actually keep the language. They among themselves they speak Tahitian and sometimes French also when they need to. Shadia is our leader, and she's the only one who speaks French. Actually, she made the whole thing happen because she speaks French. That's another long story. But the food was pretty much, it's not like here. Here we have a mix of everything, right? Asian, American, European, whatever, we throw them together. There it's primarily French and Polynesian. Okay. But the coconut is really nice. They have that. They have a big walk-in refrigerator, and they keep it cool. And when we get tired, we walk up for a coconut break, and they cut it open for you. It's really refreshing, completely organic, I'm sure. Again, the food is very French, but they tried. They actually went through an international course of manual for us. They even made sushi. So I asked, no, where did you learn to do this? She said, oh, just by the book. So it was very interesting. Very interesting. The band, they actually put up 4-5 performances for our entire state, not just for us. You can imagine the whole world wants to go there for the eclipse, right? So the tourists went there and they staged several shows for the visitors. That's the dancers. My camera was too small. My telescope is too small. It's too dark. I couldn't get good pictures, but these are the best I can get. The dock here, this, if you remember what it looks like, there's a channel from the ocean into the lagoon, but it's not deep enough for boat to go in. So their dock is on the ocean side. And this is in a rough condition. They said sometimes their boats stay out there, wait for a couple of days before it's calm enough for them to get in. And that's the only way they can transport their supply in. There's a flight in once a week, but that doesn't carry lots of stuff, right? That's the church. Most of them, I think, all of them converted to a Christianity for a long time already. Nice church, very different from what you see here or in Europe. The drawing was interesting. The graveyard, and that's there. It's on the shore. It's like I'm not quite sure why it's. Do you call it temple or something? But anyway, that's their religious life. And then the paradise, of course. After the eclipse, we finally had time to cool a little bit, and they took us to the lagoon. So we walk over to some of these little coconut islands in between the channels. It's really beautiful. And I remember I used to see those cartoons on newspapers. Some guy got stranded in this little coconut island with only one coconut tree. I thought, oh, that's nice, but that's not real, but it's almost real there. And this is a coral head. This is a mound of coral. It's like a Haleakala underwater. So we snorkel in, and it's just beautiful. It's 100 times better than snorkel on Maui, I'll tell you. The whole school of tropical fish, and you just go around with them. I can go back there. And down there is lots of these giant clams. This is a shell that's sun-bleached. They string them this like curtain outside the school. But this is what it looks like in the water. And sometimes you can see the shell here, right? And this is, in fact, if I understand it right, it's one of their major source of income. They said they are the only atoll that's allowed to export these giant clams in large quantity. Okay. So that's one source of economy, their income. The other one is the coconuts. And this one is heavily subsidized by the French government. They pay much more than market price for them to grow, and I think that's one way they support the community there. Okay, so that's the place. And let's get to about half-time. Okay, the experiment. So there are 4 groups, kind of 4. This is Shadia Habao is another faculty in the solar physics group. She lives in Manoa, and her experiment is to image the emission line corona. Emission line means emission from ions. in the atmosphere. Okay. Mostly iron, nickel, all the elements, they emit bright light in the spectral line. That's my experiments. I was going there to try to measure the magnetic field of the corona from the limb all the way out to about 1 solar radius away. And that I can never do here on the ground with our telescope up on the summit, even with the new telescope we are going to build, just because the telescope is going to give you too much scatter light. It's never really dark like in the eclipse. Right? So that's the only way I can do these experiments. In fact, I'm one of those that says, nah, why do you want to go to eclipse? And this time I finally had enough equipment. I thought it's worth trying that I can, this is one experiment that I cannot do in the observatory. And that's why I went. Silvano, a good friend from Italy, he has a group. They actually were testing a filter, an instrument that's meant to go onto that formation flight in space. Okay. This is a German company. They built telescope and telescope mount. So they were trying out the new mount they developed, very nice. So they sent their this Martin is a young PhD student, but he works in the company. It's different setup than what we have here. Send him there to do just images of the corona, white light corona, just broadband, just what your eyes would see. And the idea is they want to set up so that they can take very close-up image and then stepping out so you can get a very large region around the sun in the sky. So that's the 4 experiments. Here they have about 7 or 8 people. I have one, myself and Gary, my engineer, helping me. The Italian has about 5 or 6, and Martin has another scientist from Czech Republic, and so we have a total of 19 people there. And that's why we want to observe the corona. This is for maybe 2 weeks duration from SOHO satellite. This is what we call the white light corona, just what your eye would see if you're observing it. No filter. The sun is this big, and this is the setup is like the eclipse. You have a little disk way out front in front of your telescope. The telescope is only about, if I remember it right, a few centimeters, about an inch or so. Right? And even with that, they cannot get really close to the disk. To do that, the occulter, the disk, needs to be very, very far out, maybe 10 meters out. And even that is a problem in space. They cannot maintain the rigidity of the two pieces to make it aligned. But anyway, this is, maybe if I can restart this. No. So the sun is, we call this, you can see it streaming particles out. That's what we call the solar winds. And then you can see it puffing up. That's what we call this corona mass ejection. So they can, it's an explosive event. And the energetics, how do they happen? We have a vague idea. It's magnetic field, for sure. The magnetic field is the primary driver of all the events on the sun. Okay. But how do they happen? We don't know. How does the magnetic field evolve and change? And sometimes it doesn't do it. Now it doesn't do it very often. This is 2001 during solar maximum. So how does the magnetic field do it? We don't understand. I think that's what that's one of the planets going by the field of view. And if you watch this, the timer, 27, we started around the 10th, I believe. So this thing, when that happens, they can actually, they travel from the sun to Earth in a couple of days or so, a fast one. So it's very high-speed particles. And when they hit us, they can knock out the satellites. The currents going through the satellite would damage the satellite. And it happens a couple of times in the last 10 years that I know. The change in the magnetic field configuration of the Earth actually can induce a very strong current in our power grid. and you can knock out your power grid. It happens in mostly in northern high latitude countries, right? Canada, Norway, like Scandinavian countries. When it happens, the particles can actually go through satellite. If you are an astronaut in space station, you would want to know and hide. If you are flying the polar route, going to Asia or something, you want to know and you want to avoid that. That's when we get mutation, the X-Men, right? I mean, the high energy particle going through your gene. And so that's why we started this. And it also has, what's the other effect you can have? The communication. It can cause lots of noise in your communications. So in fact, the solar physics research in the U.S., the observatory in New Mexico, was first funded by the Air Force. Because Air Force wants to know if there's a solar events coming up. It's like our weather. We call this space weather now. Right? We don't know if we can predict when this is going to happen. And if we know it's going to happen tomorrow, then we don't want to launch a major attack because you would not have communication. Right? So that's a lot of this research was initially funded by the military, and nowadays NASA wants to know also because of the assets we have in space and also in the ground. Lots of them are very sensitive. Right? So that's why we studied this. And so the plan is to, for people from Hawaii, we leave on the 2nd, get to Tahiti. On the 5th, we go from Tahiti to Tatakoto on a chartered flight. As I said, there's only one regular flight every week, and we know it will be booked up by the tourists a long time ago. So we actually chartered the flight, and we have lots of equipment to carry also. So we'll return after eclipse is 11th, or we pack up, go back to Tahiti, come back on the 16th. This is because we only have one flight between Hawaii and Tahiti every week, right? So Friday and Friday. And we are constrained by a Fly American rule. So because this is so funded by federal money, we have to, when we fly out of the country, we have to use American carrier. So Air Tahiti Nui actually fly between LA and Tahiti every day. We have taken that flight to LA and come back. You know, we don't have to get stuck in that place for that many days. Oh well. And German and Italian, they travel separately, but that's our plan. Equipments, we have Shadia's groups. They check in their luggage. Their equipment are small, but mine is big, so I ship out early and return. We don't care. So that's a nice plan. Liquid nitrogen, we figure out how to do that already. So before I do that, I measured it carefully in the lab. We have this storage tank, so I measure them. I use 6 liters a day for the camera to keep the camera cold. The storage tank itself evaporates about 1 liter. And for this amount of days, 5 or 6 days, I figure I need about 35 liters. So I said, okay, I know how much I need. I'll take 2 50 liters tanks, dewars, from Maui. And it's because I cannot rent it there. We asked, they don't have any spare to rent. And we fill it in Papeete, then we will ship dewar to Tatakoto on boat, and it takes 10 days on the sea. Okay. So we figure out the boat schedule, and we figure we can get, the boat will get there on 4th of July. Nice day for it to arrive. And hopefully we have enough to survive for the experiment. So I double the amounts I required, right, just for sure, make sure that I have enough. Nice plan. Of course, thing doesn't work out like how you. So that's an interesting story here. Liquid nitrogen is called a dangerous good by IATA, International Air Transport Association. and it's like toxic chemicals. I don't know why, but that's what it is. So when I first asked, so why don't we just fly it, right? We are getting on a plane. It's our own plane, chartered. Why can't we fly it with our plane? I said, no, it's a passenger plane, so it's dangerous. You cannot do it. All right. But to fly from here to Tahiti, it's empty, right? So when we sent it to Hawaiian Airline, they said, how do you know it's dangerous material? How do you know it's clean? How do you wash your tank? How do you know there's no residual in the tank? Well, the residual is everywhere. You breathe in and breathe out every time. And I argue with them for a long time, and eventually they come back. I guess they then turn around and study it a little bit and say, fine, you put a label says fuel is empty on the tank, then we'll fly it. And that's what we did. Fuel is empty. And that's in the cargo hold of the passenger jets, right? All right, so that's not too bad. So we flew out on June 11th. Then supposedly, well, I thought it would go on Hawaiian Airline because it's direct flight, but DHL sent it through Air New Zealand. They have some kinds of contract, I think. Get to Auckland, then the Polynesian were on strike. I mean, it's French, right? So they strike all the time. Like every time I go there, I encounter a strike. So I got stuck in New Zealand for a week, and finally got there on the 18th. But then it's a Friday. Then they found out, well, Honolulu sent out a manifest for something else. So they couldn't get it out of the custom. And the boat was going to leave Monday afternoon, right? So, and of course they don't work Sunday, Saturday. But DHL Tahiti, they are good. They got into action, and they Monday morning they postponed. There's all kinds of paperwork they have to do, and got it out in the morning. Rush it to Airiki, and we planned it all. One of the things I didn't mention is that I knew they were metric, and we were imperial or standard, right? So I know their fitting would not fit my tank. So I actually shipped the fitting to Airiki in Tahiti way in advance. So we just hook up and go. They filled it as fast as they can, and we missed the boat by 1 hour. So that day I said, I'm not going. No reason for me to ship all my equipment there if I don't have liquid nitrogen, right? But the Tahitian said, no, hold your horses, just let us work on it. 2 days later, they convinced Air Tahiti to fly the liquid nitrogen full. I have no idea what they did, but so they said, well, we'll fly it to Tau, so the barge go to islands, right? So they get to Hao, and we will intercept the barge at Hao, put it on a boat, and then get to Tatakoto. I said, well, if you are flying, the plane goes to Tatakoto anyway, why don't you just fly it there? But then I thought about it and said, nah, don't ask for too much. Just so it got there on 3rd of July, and when I got there, we measured it 40 liters in each tank, so we were good. Right. So that was one episode. And imagine that, Shadia was on the phone for 2 days in French, talking to them, and she really, I don't know what they did, but so the preparation, of course, I worked day and night here ask my wife, 3 in the morning, 5 in the morning in the lab, and it ends up with there's a crate, a pallet here, 4 feet by 6 feet long and 4 feet tall of stuff. 10 crates, 1,400 pounds. I was crazy. Everybody said I was crazy. But, well, that's how much stuff I took there. Then Monday morning, we were getting ready for to go to Tatakoto. My equipment was good, right? It's there, clear, custom, everything. Then the Germans found out their telescope were stuck. Again, paperwork. And this time, he said, the German customs said, oh, no, this is all you need. And when they got there, no, you don't have anything. So DHL, again, come to the rescue, and they did their thing. In 2 hours, they postbound, did the paperwork, get it out, and loaded on the plane. Just 1 hour before takeoff. And this is all the stuff we were loading onto this plane, you know. And we were delayed for a couple of hours because we watched them put a big crate in, then 30 minutes later it's out again, and they were trying to figure out how to do it. Okay. There's only 2 cargo holds, one here and one back there. So one side of the airplane is filled with our equipment and luggages, and the other side is enough for us. And this is the cargo hold. I took a picture of it. And they also said we were allowed 1,500 kilograms of stuff, so that's about close to 4,000 pounds. And I used up 1,400 pounds already, plus all the pallets and all that. I used about 60% of the capacity. And so they said we can only allow for 15 pounds of personal items, and for the flight, because to fit into that, what did I say, 1,500 kilograms, right? So I end up with just my shirt and board shorts and my snorkel gear. That's very important. So we arrive in Tatakoto. You can see that's my infrared camera. Oh, this one is another story, but it's not too bad. It's an infrared camera that's dual use. So we need an export license from the State Department to take it out of the country. And we went through that and get a license. And that wasn't too bad, in fact. So we got a warm welcome. She is the winner of the singing competition last year of French Polynesia. Yeah. And again, our stuff, lots of it. They got a big truck, 2 loads to get it to the school. That's my telescope. It's home built and nothing like what you will see out here when we have a star night. So that's a close-up of the equipment. This is what we call the polarimeter. The fancy thing is this fiber cable here. This cable has 2,048 fibers in it. Cost me $130,000 to build. The idea is that it's so I can make an image of the corona and the spectrum all at the same time. It's a fancy setup. This is for my astronomer friends. We always say you got to have the photographic tape, black tape, and IBM computer cards for your instrument. Without it, it never works. So I got to have that there, and so I show this picture for my friends. The old school, right? That's the telescope, and the cable runs from here into the office. And that's the instrument inside the office. So that's the infrared camera that uses liquid nitrogen. The other view, big mirror. It's all in the lab right now, a big piece of grating. Fiber comes in here. and that goes to the mirror, go to the grating, so it makes a spectrum of the solar corona. This bench here, you take it apart, you disassemble it, and so we can transport it, right? And in the plan, so we build this. We have to assemble this whole thing in 5 days in Tahiti. It's tough, and the first thing I did there is my. I don't think it's in there. There's a light source I use to do the setup, and we, of course, again we are U.S. Imperial 120 volts. They are metric 240 volts. So we made the list of all the electronics that make sure that our electronics can dual voltage, right? And went through that. After I got there, I forgot one of the thing is 120 only. And I plug it in, smoke and fire. So the Mac light, the big flashlight, came to the rescue. Plug that in, and that worked. But that's the only thing. Oh no, that's not the only thing I burned up. The next thing is this box. That one is 240 capable. There's a switch, a chip you switch, and after we did that, it should be good. And actually, we checked with the company who built it, and they said, yeah, but nobody has ever used it, so you guys are the first. I said, okay. But they said it's all there, and it's very clear how to do it. And other equipment do that also, so not a problem. But smoke and fire. But that one was better. It has enough protection. It's only the fuse. And turns out they have some extra wire between the transformer. I haven't told them yet. I said, you guys sell me this expensive thing, and you didn't do it. But they are good guy. The company is really good. That's one minor mistake. Anyway, lots of excitement there. But we built this whole thing in 2-3 days, and that's our friendly neighbors. They just run around. So that was my experiments, and this is the German telescope that almost didn't make it. Oh, so I asked the Air Tahiti guy. I said, well, if we don't make it, what do we do? He said, we have another flight tomorrow. We'll just put it on. I said, but isn't it going to be completely full? He said, yeah, but we'll just throw some luggage out. So I don't know if he's serious or not. But so that's a very nice telescope. It's all wrapped up because under direct sunlight it gets really hot. So they wrap it up in foil. It's designed to go extreme very fast if you're an amateur astronomer. This thing can go from east to west horizon in a couple of seconds. It's designed for gamma ray burst observation, right? Somebody in space sends a gamma ray burst, give you coordinates, the telescope needs to swing and do optical observation right away. Otherwise you missed it. None of this big telescope can do it. European Star doesn't swing that fast, right? Even the Air Force doesn't go that fast. So it's a if you knows about motors, this is what we call it's a ring motor. It doesn't have a coil. No, that's not the right thing to say. But so what they do is they have two major telescopes, and they mount 1, 2, 3, 4, 5, 6. These are all Canon cameras. The Rebel or something, and they get the software from Canon, so they can program it, and they control it through their computer. So it's equipped with different focal length lenses, so it gets a different field of view of the corona. So the idea is that they want to cover the entire corona at highest possible resolution and largest possible field of view, right? And usually when you try to do that with a single camera, then the intensity near the sun is high, far away from it, the sun is low. So in a single exposure, if you don't overexpose the area near the sun, then you underexpose the faraway place, right? And vice versa. So this is how they do it. And this telescope is powerful enough to carry all this. Very nice telescope. I would like to get one. This is Manoah's experiment. Then that's a similar idea. So here we image the emission line, corona, another view. So what does it look like? Like number 5, the robot. Anyway, so these are all identical telescope, identical camera, and a very small telescope. So this is one filter on the emission line. Another one is a reference filter off band, what we call off band. So what they do is they can take images simultaneously, and they can do subtraction to get rid of the background. And if there's a cloud, it's taken simultaneously. You can subtract the clouds away also. That's the idea. In the past, what they do is they have a single filter, then a single telescope, or 2 filters, and they switch the filter. So the image were not taken simultaneously, right? So you don't never get a very good image, especially when you have some clouds. These are more sensitive in the infrared, but still CCD camera. So same experiments. This one is spectrograph, very small spectrograph compared with mine. And mine is. That's the Italian team, and they suffered some smoke and fire also. This day before I did, their mount got blown up right away. They looked at my mount and said, "Hey, it's identical. Can we borrow yours?" But they managed to put 2 telescopes on the same mount. Okay. And that's the filter that's going to go. Filter is back here. That's going to go on the spacecraft, the formation flight. That's the science team. Okay, so that's the eclipse day. 7:08. That's the sky. And somebody. I was depressed. And telescope was all zipped up because the clouds, the rain were coming after there for a few days, we know. Sure enough, so the Italian, they are smart. They have everybody hold up a big piece of plastic and just, so they have enough people. I only have 4 hands. So I got it all bottomed up and covered up. We got shadows, right? That looks pretty good. 8:15. Opened up, ready to go. Not really. So the sun is here, but you see the partial eclipse now, right? So where is the sun? Is this the sun or that? Is that the sun? This is your camera. The sun is here, but it's so bright, and the multiple reflection inside your optics give you this one, so you can see a nice partial eclipse there. Well, but if you're an observer, you know the target you want to look at is always cloudy, and other places are always clear. So that's to the west, to the west. So I took that picture. Never fail. So this is about 15 minutes before. You can see the partial eclipse. That's the fiber input. So we put the fiber on the east limb of the sun. This is the limb of the sun. So the west limb of the sun got covered first, so this will go narrower and narrower. So we did our pointing. We wait for it. And I was so used to do this on the computer that I was really confused about my pointing. So I have to put east, south, west, north, and use hand pedal. It's really confusing. And this guy was really good. So everybody just run around. This is my $130,000 cable. And I noticed when he come across, he stopped, get off his bike, pick up his bike, step over, and then go. So I got to get a picture of him. He's a nice guy. We can still see the clouds. 18 seconds in the clouds. That's second contact. Briefly. And then that's a movie from my precisely guided video camera. So I sneak out of the lab and take a 45 seconds sequence. And you can see the clouds going by all the time. So, that's when I snap a picture, still picture, so it stopped. But anyway, you can see the condition is really not optimal. Well, but we managed to get some nice pictures. So remember, these are imaging. So they take exposure a few 10 milliseconds, right? So very short. And so you can still get some nice picture. And this is from the largest field of view of the German instrument, this telescope. So the shortest one, right? Nice view of the solar corona. You can see all the streamers coming out. And that's another telescope getting closer. Well, why do they look so different? Right, that's my video camera. That's their fancy telescope. They doctored it. Right, so the original image looks like this. So you can see the brightness falls off very quickly away from the sun. So your eye cannot see all this fine structure within this background. So this is processed. They remove this gradual fall of the background, so you can see the fine structure in the corona. Okay. Again, closer, you start to see a lot of details. That's nice. And there are some fancy mathematics algorithm get into this to process it. And you can go to this. I don't have the website, but this is all on the web. If you like, I can give you the web address. And they have, they didn't really explain the mathematics of how they do it, but they said they salvaged only a few frames to make this sequence. Otherwise, we would have a nice movie of it, right? But that's the advantage of imaging, that you can take a snapshot and work on it, right? And if you have a brief moment of uniform clouds, not even wishing for a completely clear sky, uniform clouds, then you can work it out. So here you can see all this structure. I think the next one is even closer, right? All this loop structure, the sheet. This. Imagine if you can watch a movie of this, the magnetic field turning, right? So these loops are all magnetic field. They trace the magnetic field structure in the solar corona. So the magnetic field can affect the temperature and density structure in the solar corona, and that change the brightness of and how we see it there. Right. So the idea is that these loops, when the magnetic field reconnects, and they can, two independent loops, they can reconnect. When they do that, they release magnetic field energy, and that energy can actually drive the electrons, the charged particle, and accelerate them to a very high speed and send them out. Right? That's the idea, but we need to observe them and make sure that's what's going on. And that's a very difficult, well, even I think next generation is still going to be a very difficult observation to do. Because we need to get spectrum, not just images like this. And that's what my instrument was designed to do. My instrument can take images and spectrum all at the same time. From the Manoa team, what they do, this is a regular H alpha. H alpha is the hydrogen absorption line in the red wavelength, 600, 500, 6,500 nanometer or so. So this you see very often. So nothing too exciting here. It's not a hot corona. This is the cool part of the atmosphere. These are highly ionized iron. Fe is iron. So it's let me see, 9 times 9. That's 8 times ionized. So that means 8 of the electron in the iron atom was stripped out. So the iron atoms now is charged. It's stripped out because of the in the light knock out the electron. It's ionized that way. So according to Shadia, this is the first time anybody has taken an image in this particular line. Okay, and they were going after some lines that was not observed before. This is another one, Nico, 15, so that's 14 times ionized. And you can see there are some. They looks very similar, but if you look at it very carefully and try to see the difference, then there are some differences. This line exists in different temperature. Okay. They are excited at different temperature regimes. So the difference actually tells you something about the temperature in the solar corona. This is a classic line, 9, we call the green line at the 530 nanometer. Again, you can see the structure now is slightly different. Another one, iron line again. Okay, that's Shadia's data. That's my experiments, and I got this. After it was over, went to the computer, look at my data, I saw nothing. It's one of the things, this is going to be one of the mysteries in my life that I can never explain. I thought, well, we did everything, everything checked out before the eclipse. We just, when it started, we hit go, and then the computer take over. So at first I thought, oh, must be telescope is bumped. It's looking at the wrong place on the moon. The moon is the darkest part of the sky at that point. Or did I was looking at the disk and watching the limb of the moon going by. First, I thought I must have forgotten to repoint the telescope. But then earlier there's a picture that shows I actually put it to the east limb. That picture came from Gary. A month later, hey, look at this picture. No, you pointed it to the right place. I wonder what happened. And we were, after the eclipse, we were taking calibration data, and everything still looks fine. Everything works. So until today, I don't know. My only possible explanation is that the clouds were thick enough that I'm working in infrared. That maybe the clouds was thick enough to block all the infrared light, but I don't think that's the case. So I'm still wondering what happened. I cannot explain it. After all the work, it was really disappointing. But well, this is an observer. We get lucky enough to see the solar corona. My best records, best or worst records when I was on the telescope in Mexico was 21 out of 23 days cloudy. So I have a reputation of being the cloudy man. But my luck has changed recently, but this one didn't work out for me. Anyway, but, so I like to say, I don't know how I become an astronomer. I started out as a physicist, and I think physicists, we go into the lab, we manipulate things, we make it do that. So we play God, right, in the lab. But as an astronomer, you sit there, you are at the mercy of the guy up there, so you play with God. And you have to be happy with what you get. And sometimes you get lucky, sometimes you don't, and we try again. Right? So So that's my my experiment. And you've been here with liquid nitrogen ice cream, I'm sure. So we have some left. I thought, what do we do? And for our hosts, I think it would be some wonderful experience. So the dinner, before we left, we took it out and we started to make ice cream. Put it into a thermos. We're stirring it, and we didn't have the fancy setup, protective glasses, everything. I'm sure OSHA would put me in jail for doing this, but the locals are, I mean, they are happy. They got to see it. They can see all the curious people. So it was good blast. And we made some ice cream, and then we tried it on the coconuts also. The coconut actually holds the liquid nitrogen very well. Yeah. So you just want a real cold coconut. When I first got the tank here, we were having our party and warm beer. So what do? But if you are not careful, it freezes right away. So it takes a long time to throw it out. So anyway, so we had some fun, and for our farewell. And so that's it. This is a flyby of the islands when we got there. I thought we were going to land, but the pilots actually give us a 360. So it takes a few minutes to go through this, but that's the island. And so that's what I prepared to show. And so with that, I think I can take questions if you have any. Yes, sir. Thank you.
What wavelength was your infrared camera sensitive?
That one is sensitive to 2.5 micron. It's from 800 to 800 nanometer, or 0.8 micron to 2.5. At 1 micron, the spectral line I was looking at, the water vapor absorption was not strong. It's one of the windows, the J-band windows in the infrared spectrum. So water vapor absorption is not very particularly strong there, but it's cloud. If you know. Yes.
When are you going to do another solar eclipse experiment and where?
Well, the next one is 2012 in Australia, November. It's short. Well, it's 4 minutes also. But you need to get out into the ocean, and then it's really difficult. On land, we get about 2 minutes or so. My experiments need every second in that duration. My experiments cannot just take a single image and say it's good. You need to add all the exposure together to get the sensitivity I need. Okay. So I don't know if it's worth it, but somebody said, well, you need to prove it will work. And this experiment only worked so far 2 times. It's a new experiment that we developed the technique to do it, and I did it twice. And this is the first time we tried it in the eclipse. So I don't know. The Manoa group, they are going for sure. They go to everyone, but I don't know if it's worth the risk, and it takes a lot of money to do it. And if I were to do it again, I would redo the instrument so that I can set it up here in the lab and pack it up without touching it, ship it there, open it up, and run. So that it takes a lot of preparation and to make it work. So I don't know yet. Yes? Yes?
How much did all the stuff cost to ship it?
Oh. The infrared camera itself cost about $300,000 to build. Together, my equipment cost about $600,000. all the equipment I took there. And the thing I didn't expect was the insurance cost for the shipping, and it doubled the shipping cost. We paid close to $10,000 just for the insurance, and I cannot afford not to insure them. Right? So these are all very specialized equipment, and cost a lot of money to build. And this is all. The camera is not very special because we have a lot of them on the big telescope now. Right? But some of them, like the fiber, it's special. Yes, sir?
Besides pre-assembling, like your whole setup before you send it, so you don't have to do it there, are there other changes to your experiment that you're looking to do?
For this particular setup, I think if I were to do it again, I would build a instrument crate that I can do all the setup here, and that I can take the hardship of the shipping and survive there. And believe me, they are really rough on this equipment. They play football with it. You won't believe what they do with it. We packed ourselves going out, so all the equipment survived without any incidents. On the way back, we gave it to DHL Tahiti, and they broke quite a few things on the way back. Yeah. Yes. I don't have it here right now. If I can give it to you after. Yes, sir.
On the photographs of the corona that we were showing, there appears to be a halo around the sun, around the moon, a series of rings. Is that anything? Is that just an artifact, or was that actually?
Let me see which one.
Not the closest one of the ones you did, but in between distances.
Is it the background? This one?
Now go back further into the imaging. It was, I think, the Manoa imaging.
Oh, okay. Let me get out of it.
Yeah, there appears to be circular patterns around and not uniform. But
Circular pattern around. You mean?
the halo action.
Look. You mean like
Is that a diffraction?
this?
No, just outside the moon, the brain.
Yeah. This one is processed also. So I think the processing can be introduced. Yeah. Yeah. And I think this thing that certainly is this is from, I think they processed in the hotel there. Some of this image. So this is all very preliminary. Yeah. Yes.
Why does it seem like the action is always sort of going horizontally like that?
Yeah. So if in this image it's aligned so that the rotation axis of the sun is up and down, it's north and south pole. So if you know the sun has a active region, active latitude, right? So the strong magnetic field are all concentrated around 30 degrees north and south. So all this are strong magnetic field region, and the streamer all goes out like that. And if you have better resolution, you will see tiny thread going straight up. We call it the open field configuration, and but they are much weaker in intensity, so you don't see them very well in this image. Yeah. But that's a typical configuration for the sun.
And those weak streamers seem to come back?
No, we cannot trace them that far. Right? Magnetic field got to reconnect back. There's no monopole, right? So they come out. In fact, some of them come as far as Earth and reconnect with Earth's magnetosphere, right? And then it goes further out, and interplanetary space, interstellar space. Where do they connect? We cannot trace them. We don't have the technology to do that, right? But on this, in some of these cases, like let's see, from these high-resolution images here, then you can see this loop structure, right? Then that's how magnetic field reconnect back to its surface. So when this open up, now the charged particle want to follow the field line, and that's how they can stream out. And the streaming of the particle out is what we call the solar winds, and that's what makes the comets. The solar wind is pushing against the comets and stripping the material. So the comet's tail always point away from the sun. Doesn't matter which way it's going. Right? The tail doesn't tell you which way the comet is moving, and that's because of solar winds. And in one of the movie that you see all these particles streaming out, right? And so that's you can see a lot of detailed structure here. That's an amazing image. I was surprised that they pulled this out because looking out, saying, if I didn't get it, you guys won't get anything, but they did. So it's great. Yes, sir.
There's you have the stereo satellites and SOHO and all these other ones going around. Is there anyone trying to put this data that you find in the Eclipse and see, synthesize between all these various data streams?
I'm not aware of any coordinated efforts. SOHO, well, nowadays stereo.
Right.
Stereo is if it's two satellites. Now I think they are 90 degrees apart. So one of the limitations of we are bounded here on Earth. We can only look at the sun in one direction, right? So we only see this face of the sun, and whatever we look at, we don't know where it is along the line of sight. The stereo mission is designed to have two satellites, one looking at it this way, the other one looking at it this way. So it's triangulation. Then you can look at the structure and reconstruct the three-dimensional structure of the corona. Right? So that's stereo. This data set is much higher resolution than what stereo can do. And stereo doesn't get so close to the limb of the sun. The coronagraph on the spacecraft, it's really difficult to get really, really close to the sun. Right? So what kinds of science can we do combining this with stereo? I think there are something, but the purpose of the strength of the stereo is a three-dimensional structure and the evolution of the solar corona. This is snapshot. So it tells us a lot about the detailed structure, fine structure that we don't see in the spacecraft. But to combine them, I don't know. I have to think about it. Some people may be thinking about it already.
And that's a multi-spectrum. The stereo, multiple frequencies.
Yeah, stereo has several instruments on it. One is telescope looking at white light like this. Then there are several, another telescope that look at the emission line corona in the UV, actually, in UV wavelength. And so, yeah, it has many different instruments on it. Yes.
Why isn't the Earth in the center of the moon's orbit? Is the sun pulling the moon out?
The sun is not pulling the moon out. It's a gravitationally, it's a bound state, right? The sun is very big, but the gravitational strength of the sun, because it's so far away, the gravitational pull of the sun on the moon actually is weaker than the gravitational pull of the Earth to the moon. Distance, right? The gravitational force decrease as a function of the square of the distance. So it drop like the way to say it. Right? So that's why the big galaxy way over there, that's hundreds of billion times more massive than our Earth, but we feel mostly the gravitational pull of the Earth. Right. So, yes, sir, you have a question?
I'm just curious, how dark is it during the eclipse? Are the stars out?
Oh yeah, the stars are out.
Is
Yeah.
it like a full moon day, or night?
It's almost like a full moon day. Yes. The brightness of the moon is comparable to the brightness of the moon. That's when I was in school. That's the rule of thumb. But I was thinking about it today and said, no, there's something is off. But it's comparable. So usually when we go to the eclipse, before it really happens, we use the moon to calibrate, to figure out how much exposure time we need so we don't overexpose. And we use the moon for that. I was thinking about it today. I said, no, that doesn't make sense because you can see the moon during the day, right? But you don't see the corona during the day. So moon is a little bit brighter. Yeah. But we need to do a real measurement to settle this one. So, yes?
Did you do any astronomy when you were living in Taiwan?
Little bit. I was a physics student, but I was interested in astronomy from very, very young. And so I look at the star, I go out and lie down and identify the constellation and all that. But I didn't plan on astronomy for a career, but anyway, it happened. So, yes.
You talked about the supplies on the island. Was fresh water plentiful on the island? Did you gather it when it rained?
It's catchment. Yeah, so it rains a lot. I think it's El Nino this year, so supposedly it was supposed to be a dry season, and it rained almost every day. Because before we went there, we asked people on Tahiti. And Tahiti was raining every day, and we asked them. They said, "No, Tatakoto should be fine. It's dry." Yeah, it's El Nino. We know. We didn't know before. Right? So. Well, but that's the life of an observer. You take what you get. Thank you very much. So, the web address.
Good to see you, Marty. Nice job.
Thank you.
Graham. Thanks.
You're welcome. Oh, thank you.
Thank you very much.
Oh, you're welcome. Thank you for coming. Thank you.
Yeah, exactly.
If you know how to run telescope, I'll take you. Thank you very much.
You know, there's a story about Wolfgang Pauli, Pauli principle.
Uh-huh.
He went to Switzerland to see an experiment, high vacuum experiment back in the 30s that they set up just for him to see. He came by train, arrived in there. The experiment was broken.
Broken. Oh.
They found out it was a vibration from the train coming into town.
His fan.
Broke the